Hello, everybody. This is Giovanni Gambirasio from Selecti, and I'm very happy to share with you this real case study focusing on internal review process for protection relay and coordination studies. Before start with the case study, I want to give you a quick overview of the electrical power system that basically consists in an existing FPSO, IC rules 50 Hz, that is normally supplied by 3 independent gas turbine generator and fed by 11 kV switchgear with various medium voltage and low voltage load. And the brownfield expansion consists in a new substation with dedicated medium voltage and low voltage load. So our main target is to perform the protection relay coordination. And personally, my personal task over this project is to review the protection coordination study performed by our protection engineer. So basically, my target is to verify and validate the proposed setting, both from protection and coordination perspective, and to make sure that approved and coordinated consistent protection device coordination criteria are met. And as well, I'm trying to track, report setting modification, and so on. But before proceed, let me go on ETAP interface. And I want to briefly show you the electrical power system. So we do have 3 generator, medium voltage system, low voltage distribution, and especially we do have the new loads and new substation. Mainly consist into in-camera by cable, connected 11 kV, the medium voltage switchgear, 4 independent asynchronous induction motors, medium voltage to low voltage transformer, and various loads. So the first step to perform a review of protection relay coordination is to make sure to assess the maximum and minimum fault level. So also the tripping characteristic of protection should be compared with. So let me utilize a scenario wizard to run firstly the minimum short circuit that I have pre-configured earlier. So I want to identify the minimum fault level, both medium voltage and low voltage. Minimum fault level obviously will be very impacted on medium voltage due to we are going to consider 1 only generator instead of 3, neglect motor contribution and so on. And we are in the order on 7.5, 7.6 kiloamps at 11 kV and 34 kiloamps in low voltage system. While if we perform the maximum calculation, we definitely increase the fault level on medium voltage up to 37 kiloamps, and then as well on low voltage system. So this first investigation allow me to have a feeling on the system and understanding on the prospective short circuit level. But let me switch on another presentation. So the presentation has been prepared by our protection engineer with the scope to identify more in detail all the protection that are installed in this new substation, new load. Basically, for the in-camera, we do have the phase and ground protection with the phase and ring CT. We do have the cable differential protection. We have the bus type protection, all the individual medium voltage outgoing feeders with the relays and direct relay connected to phase and ring CT. We do have on low voltage in-camera body relay connect on the in-camera feeder and as well as start point of the transformer and so on. So the first step that I want to ensure that the protection are already fitting the model rightly. For example, if I double click on the protection in the model, I want to make sure that all the input in terms of CT, ground CT, phase CT, output in terms of which one circuit breaker we want to operate in case we detect a fault condition. I can, for example, select a portion of a system and I can utilize this automated function that basically verify the design device assignment. So give me a lot of informative information, such as I didn't enable jam protection, overload acceleration protection, and so on. But what I really care more is the alert and warning. And in this case, what's the alert is there is no VT assigned to this protection. So for the purpose of parametrical relay coordination, we don't need to have effectively this connection in ETAP, so we can jump on and we can apply the same type of approach by selecting a widely portion of the system and again run this automated function try to ensure ourselves that all protection are positioned well in ETAP. So input, output works out and so on. So I can really double check and see mostly of the information warning are related to assignment of VT. And we have a couple of alerts. And if I click here, automatically bring me to the dedicated breaker. So the message is basically that inside this breaker, we didn't enable a trip unit, but this is normal and consistent with our installation because we already have an NDR relay that is going to send trip command to the breaker. So everything is worked well. So also I have the feeling on the short circuit level, maximum, minimum. Also have the feeling that all the protection are properly put inside the tool with the proper input and output. I can start to go deeply into the setting. So I can double click one by one really and check the setting, or I can use the functionality that ETAP already provide me. So automatic detect the zone of protection of this motor, for example, and automatically allow me to create a TCC drawing, including all the zone of protection. So in this case, we are speaking about motors, cable, CT, circuit breaker, and dedicated protection. So let me zoom a little bit on this area to see what is the element shown by the TCC drawing. So basically we have the motor transient behavior under starting at full voltage and reduced voltage, obviously full voltage higher, locked voltage current and shorter starting time, and obviously the opposite, the reduced voltage. We do have the motor withstand capability. We do have the cable short circuit withstand capability along the opacity of the cable, and you can obviously visualize or not the various items, and the protection characteristics. So from the thermal load to the short circuit protection. And we can even easily quickly delete this TCC drawing and go back to our system to start to identify not only the protection, but also the coordination. So let me do a very similar exercise. I'm going to select this transformer. Once I have selected this transformer, I can automatically select by this option, protection zone viewer, the zone of protection, so primary and secondary side, and automatically generate for me TCC drawing. So I can again compare the characteristic of the equipment, such as in this case, the transformer, the inrush characteristic of a transformer, the withstand capability of a transformer, and the primary and secondary side protection. So we can assess protection and we assess coordination as well. We can use all the functionalities such as time gap verification to verify what's going to be the time gap selected by our protection engineer, and so on and so forth. So those are actions that can easily and quickly do. So create TCC drawing wherever I need, whether I believe comfortable for me to identify the setting. And now I want to go a little bit more in detail to see what is the actual TCC drawing created by our protection engineer. So the purpose is not only to verify protection and coordination, but as well the deliverable that we are going to issue to the customer. So here we have the transformer, primary and secondary side, with all the setting and so on. We do have the large motor characteristics. So we don't only compare the motor with its protection, but as well with the upstream protection, means bus tie. So once I click this blue one, automatically highlight to me this bus tie. And in this case, I'm going to see the in-camera. So looks properly, coordination between protection exists. And I can go to the other motor, it's a little bit smaller. And here I can notice that, for example, we have a level of inconsistency. So the tripping characteristic cross the starting characteristic. So it's probably need to put some adjustments, some modification. So the action that I'm gonna doing to apply this modification is operate with the data managers and in particular create a new revision. So basically by creating a new revision, we create a second data set of data. So means that all the equipment, several equipment, or only one equipment can have a different input data. So we are not going to use to modify the data of motor, transformer, equipment, and so on, but the target here is to modify the setting of some protection, adjust those settings so we can still have the older version of protection reading coordination studies and setting, and we can have the new version of rotation coordination setting. So that's the main purpose of revision that perfectly match with this and my target especially. So in order to proceed, I want to use another instrument that we have available in ETAP. So again, let me select this motor. What I can do, I can just click here on the start out evaluation. So start out evaluation is the possibility to automatically compare the setting with the predefined criteria, rule, and so on. So the idea is to compare automatically all the settings that I have already inside my protection coordination. And once I can compare, I can verify that there is consistency between the criteria and selected criteria. So for this motor, we see that everything is green, so everything is approved, and automatically ETAP generate for me the various cards, so I can go in detail of the motor and have all the characteristics of the motor versus all the various criteria that I have included in my rule books. The same is going to be for the cable. So we have, again, a proper protection of the cable. And I can select, for example, the second motor. That's the ones where we notice the risk of inconsistency between the protection and the starting characteristics. And here I'm going to expect some bad flag, and this is what can happen. So what I can do right here, since it's motor, I can go to the motor and see a little bit more in detail. And I can go in the motor, double click, and obviously I can change manually the settings, or I can go here and automatically move by hand the settings. And ETAP, for me, once you have enabled this continuous evaluation, verify that the new protection criteria, the protection setting meet our protection criteria. And again, we want to see, and what we see, that the protection are well designed. And if you go back to general, we see that both status is going to be green. So this is very useful because it's online correction, online modification, and so on. And even visually, I can see that this really has a different color, have a different highlight, a little bit bold. So we can immediately notice, see what's going to be the difference. So in a similar way, I can select the entire connection of this transformer and again run the start out evaluation. So by this way, we are not only limited our analysis to the protection of the transformer itself, but we are going to investigate as well the coordination between upstream and downstream protection. So let me a little bit expand again, and we are going to have some issue on the transformer that does not pass protected device evaluation. So let me move on the transformer. On primary side, we see that everything worked well. So the green curve seems matching with our criteria. On secondary side, instead, we find apical leaping inconsistencies. And the reason is mainly that the setting is lower than transformer full load M. So it's very, let me say, marginal error. It's very complex to notice here in the card, but by benefit of the protection start out evaluation, you can very quickly and roughly control, verify everything. So for the transformer, this maybe happen very infrequently, this type of mistakes, but for motors, you maybe update a little bit data, efficiency, power factor, and so on. So the rated current of the motor, for example, is changed minorly. You can have similar type of issues. So with start out evaluation, you can easily compare if your predefined criteria that could be, for example, a percentage range from the full load amps in which you want to have the setting is matching or not. So once we noted the transformer, we have the full protection and we are happy. The similar way for the cable, primary and secondary side, we can have a look at the coordination. So coordination automatically verify for us if there is consistency across primary and secondary side. In terms of phase, 3-phase, we see full consistency, and the coordination depends really from your rules, but we integrate rules that verify coordination in terms of time grading and in terms of current grading, so both match. For zero sequence, line to ground, it's not evaluated, and it's just a flag, but this is pretty much obviously because we don't need to verify coordination between systems at different homopolar levels, so due to the coupling of delta star transformer. And we can apply the same type of rule, methodology, and philosophy just by selecting a larger portion of our system. So basically, all the entire system that we do have. And once we have selected, we can run the start out evaluation, and we can have in one click the complete evaluation of the entire system. So what's most of the benefit of this is to have a very controlling technique, a similar way to verify the setting and protection across the various devices. So similar technique, same technology. We can have an immediate view of the various alert, flag, and so on, and we can easily expand and verify one by one the element. So let's have a look at the motors. For example, what we see here, the motor, we have some issue here, and one of the issue can be easily solved by modify the setting curve. So it's really online correction and modification. This is one of the benefit. One of the second most important benefit, then whenever you change some setting, and in this case, our setting was changed and approved, a setting change could be lead in an issue in terms of coordination. So here we are continuously and simultaneously controlling, checking protection and coordination, so we can ensure that both things work well. So we can go one by one to the motor and solve the issue, and the same on the transformer. If we have some issue, it's going to be the same issue that we have seen for transformer A. Here we are noticing transformer B, and we are going to apply modification and correct. And again, ETAP will generate updated TCC drawing, updated table and control, and so on. So everything is going to work well and to verify protection and coordination. So from coordination perspective, we can see some inconsistency. So let me filter phase protection firstly, and we see that generally we have a good matching. So in this case, we are observing a miscoordination, and the miscoordination is served between primary and secondary, so upstream and downstream, and this is going to be the 11 kV feeder connection. So there is missing chronometrical time delay. So especially it is going to work on this area, but we know it, and we know that for the light protection, we can even don't have coordination between primary and secondary side, because if the fault is in the cable, we have differential protection. So in any case, we can delay the fault coordinately and selectively, and anyway, it's a feeder connection, so trip of upstream, downstream will be reflecting the same element. So I really have and used all the instrument to go through this protection coordination. I can easily see even visually what I have modified, adjusted, and so on. I can obviously even export this start out evaluation in terms of report. So it will be very, very useful. And you can see here, or you can export as evaluation report, and you can really put it in a spreadsheet, all the settings, all the comparison between the settings and the result of the comparison. So if it's passed and not passed and so on. And for sure, you can go through a device setting report and properly export all the settings that you have in your database. So you can easily go through, track, verify, and complete your internal review of protection device coordination. So going back to my slide, let me move on the conclusion part of my presentation. In terms of case study conclusion and project outcomes, so the existing greenfield protection settings, the new setting has been properly selected and allowed to achieve protection and coordination. And this came at the end of the entire process of preparing setting coordination and review. We have done a complete protection device coordination validation across different conditions, full level, and so on. We ensured that approved protection device criteria were met. So that's especially thankful to the STAR out evaluation and the internal review that was basically my task was effectively concluded with the necessary tracking and report that we need. So what are the ETAP support that give to me under this task? So that's mainly what are my preferred solution capability for this case study. So first of all, we can use a single power tool for multiple solutions. So we can run in short circuit, identify multiple configuration, study protection, out evaluation, and so on and so forth. We have a systematic approach. So by using the rulebook, we are going to use every time the same rule, the same criteria, the same parameter that we are going to check in. We can very quickly do online correction, modification, and the calculation. Allow to me in a combined tabular and graphical view to have a complete understanding of the system. Very useful, the automated protection zone identification. So automatically identify the zone of protection of each given for motor, transformer, cable, and entire system. And for sure, we can benefit to the multiple configuration and case study support. So thank you for attention. I was pleased to present this case study along with you. Bye-bye.